What if I told you the universe left us a message, an ancient, glowing fingerprint from the very moment of its birth? Etched into the fabric of space itself, this cosmic whisper is real, and it's called the cosmic microwave background. Picture this, a faint afterglow, colder than the deepest reaches of space, stretching across the entire sky. It's the oldest light in existence, a snapshot of the universe when it was just a newborn, barely 380,000 years old. But here's the astonishing part. Hidden within that light are 24 cryptic clues, like cosmic breadcrumbs leading us back to the Big Bang itself. This isn't just radiation, it's a time capsule. Every ripple, every faint variation in temperature tells a story. Some of these patterns hint at invisible forces like dark matter, weaving through the cosmos like ghostly threads. Others suggest the universe expanded faster than light in its first fleeting moments, a theory called cosmic inflation. And then there are the whispers of something even more mind-bending, parallel universes, bubbling beyond the edges of our own. How do we know all this? Because scientists have learned to read the cosmic microwave background like a language, translating its subtle signals into revelations about where we came from, what the universe is made of, and even how it might end. But why should this matter to you? Because this isn't just about distant stars or abstract physics. It's about the ultimate origin story, our story. The cosmic microwave background is the closest thing we have to a blueprint of reality, a map that shows how everything, from the atoms in your body to the galaxies spinning billions of light years away, came to be. And today, we're going to crack that code together. We'll explore how this ancient light reveals the universe's secrets, from its explosive beginnings to its mysterious future. So settle in, because by the time we're done, you'll never look at the night sky the same way again. The cosmos is speaking, and we're finally learning how to listen. Think of the cosmic microwave background as the universe's first baby foe, except instead of a chubby-cheeked grin, it's a grainy, black and white image of reality itself taking shape. That faint glow you see. It's the last echo of the Big Bang's fireball, captured when the cosmos was just a toddler at 380,000 years old. Back then, the universe was a swirling soup of particles too hot to form atoms, a chaotic fog of light and matter. But as it expanded and cooled, something extraordinary happened. Electrons and protons finally linked up, creating the first hydrogen atoms, and in that moment, light broke free. That flash, the very first light, has been traveling across space ever since, stretched by the universe's expansion into the microwave whispers we detect today. What's astonishing is how smooth this ancient glow appears at first glance. Imagine pouring milk into coffee and stirring it perfectly, no clumps, no swirls, just seamless uniformity. That's how the early universe looked, with temperatures varying by less than 1 part in 100,000. But those tiny imperfections, they're the universe's secret ingredients. Like invisible brushstrokes on a canvas, these slight variations in density and temperature were the seeds of everything we see now. A fraction more matter here, a whisper less there, and over billions of years, gravity amplified those differences, sculpting galaxies, stars, and eventually planets. Without those subtle flaws, the cosmos would be a vast, empty sea. No structure, no life, just endless sameness. And here, where it gets even wilder, scientists didn't even set out to find this cosmic fingerprint. In 1965, 2 radio astronomers, Arno and Robert Wilson, were troubleshooting a persistent static in their antenna, a noise they blamed on pigeon droppings at first. After scrubbing the equipment and shooing away the birds, the hum remained. That noise turned out to be the universe's oldest light, a discovery that earned them a Nobel Prize and rewrote our understanding of cosmic origins. Today, satellites like WMAP have mapped this glow in exquisite detail, revealing patterns so precise they act like a cosmic barcode, encoding the universe's weight, age, and even its fate. So next time you gaze up at the night sky, remember, those twinkling stars and swirling galaxies owe their existence to those faint ripples in the cosmic microwave background. It's the ultimate family heirloom, a relic that connects us directly to the universe's fiery birth. And this is just the first clue, because as we'll see, this ancient light holds even deeper mysteries waiting to be unraveled. Those tiny temperature fluctuations in the cosmic microwave background, those millionth of a degree hot and cold spots, aren't just random noise. They're cosmic hieroglyphs, telling us exactly how the universe sounded in its infancy. Imagine the early cosmos as a vast, echoing chamber, filled with pressure waves rippling through the hot plasma like through air. These primordial vibrations left their mark on the CMB, imprinting a pattern so precise it acts like a fingerprint of the universe's very first moments. What's incredible is how these microscopic variations became the blueprints for everything we see today. Picture dropping a pebble into a still pond. The ripples spread outward, creating peaks and troughs. In the early universe, those peaks were regions where matter clumped together just slightly more densely, while the troughs were emptier patches. Over billions of years, gravity amplified those differences, pulling more matter into the dense areas until they collapsed into galaxies, while the voids grew even larger. That's why today's universe looks like a cosmic web, filaments of galaxies strung across vast, empty spaces. The hot spots in the CMB, those are the seeds of superclusters. The cold spots, the future homes of nothingness, voids stretching millions of light years. Satellites like COBE, WMAP, and didn't just detect these fluctuations. They mapped them with astonishing precision, revealing patterns that match theoretical predictions almost perfectly. It's as if the universe handed scientists a cheat sheet. For example, the spacing between hot and cold spots acts like a cosmic ruler, telling us how fast the universe expanded in those first critical moments. The closer together the ripples, the more tightly packed the early universe was, and that spacing matches exactly what we'd expect if cosmic inflation, that brief period of faster-than-light expansion, really happened. But here, where it gets even stranger. These temperature variations also reveal the universe's ingredients. By studying how matter clumped together, scientists could weigh the cosmos, and that's how we discovered most of it isn't even made of the stuff we can see. Ordinary matter, the atoms in stars, planets, and us, makes up less than 5% of the universe. The rest is dark matter and dark energy, mysterious forces that shape those primordial ripples in ways we're still deciphering. Without dark matter's gravitational pull, those early density fluctuations wouldn't have grown into galaxies. Without dark energy's push, the universe wouldn't be accelerating its expansion today. So when you look at a CMB temperature map, you're not just seeing static, you're reading the universe's diary. Every blotch of heat, every patch of cold is a sentence in a story that began 13.8 billion years ago. And this is just the second clue, because as we'll see, the cosmic microwave background has even more secrets to share. Those faint ripples in the cosmic microwave background aren't just silent imprints. They're the echoes of the universe's first sounds. Picture the early cosmos not as a void, but as a seething ocean of plasma, so dense that light couldn't travel far before bouncing off charged particles. In that superheated chaos, pressure waves surged through the cosmic soup like through water, compressing and rareifying matter in rhythmic pulses. These weren't gentle whispers, they were thunderous vibrations, propagating at half the speed of light. And when the universe cooled enough for atoms to form, suddenly freeing light to travel unimpeded, those waves froze in place, etched into the CMB like grooves on a vinyl record. What's astonishing is how much these acoustic oscillations reveal. Just as a musical note tells you about the instrument that created it, the tension of its strings, the shape of its body, these primordial encode the universe's fundamental properties. By measuring their spacing and amplitude, scientists can reconstruct the exact proportions of ordinary matter, and dark energy. Think of it like cosmic forensics. The spacing between peaks in the CMB, the more matter was present to slow those waves down. The height of each peak, that's a clue about how much dark matter was pulling everything together. Even the relative strength of the third peak versus the first reveals the density of ordinary atoms, the stuff that eventually built stars, planets, and us. The precision is staggering. These oscillations act like a universal tuning fork, vibrating at frequencies that match theoretical predictions down to a fraction of a percent. When researchers analyzed data from the satellite, they found the first peak corresponded to a universe made up of about 4.9% ordinary matter, 26.8% dark matter, and 68.3% dark energy. It's as if the cosmos left us an exact recipe, and every ingredient measured to the gram. But here's the real magic. These also tell us about the universe's shape. Just as sound behaves differently in a small room versus a cathedral, the way those primordial oscillations propagated reveals whether space is flat, curved, or closed. The CMB's peaks strongly favor a flat universe, one where parallel lines never meet, and the angles of a triangle always add up to 180 degrees. That flatness, in turn, supports the theory of cosmic inflation, that explosive expansion in the universe's first fraction of a second. So when you hear scientists talk about listening to the universe, they're not speaking poetically. Those faint temperature variations in the CMB are literally the fossilized vibrations of reality's first moments, a symphony written into the fabric of space itself. And just as a composer hides themes within a musical score, the universe embedded its deepest truths in these oscillations, waiting for us to learn how to hear them. One of the most baffling mysteries hidden in the cosmic microwave background is something called the horizon problem, and it challenges everything we thought we knew about how the universe communicates. Here's the puzzle. If you look at opposite sides of the sky, the CMB's temperature is nearly identical, varying by less than 1 part in 100,000. But here's the catch: in the universe's early days, light shouldn't have had enough time to travel between those regions. Think of it like two people standing on opposite ends of a stadium, each holding a sign that says the exact same word, even though they've never met or exchanged a single message. How could patches of space so far apart have coordinated their temperatures so perfectly? This is where cosmic inflation comes in, a theory so radical it rewrote our understanding of the Big Bang. Imagine the universe in its first trillionth of a second, smaller than a single atom. Then, in an unimaginably brief burst, it expanded faster than light itself, stretching quantum fluctuations into cosmic-scale ripples. Inflation didn't just make the universe bigger, it ironed out its wrinkles, explaining why the CMB looks so smooth today. Those tiny temperature differences we see, they're the stretched-out remnants of quantum jitters, microscopic variations amplified to galactic proportions. But inflation isn't just a clever fix for the horizon problem, it's a prediction machine. If the theory is correct, the CMB's fluctuations should follow a very specific pattern, one that satellites have confirmed with jaw-dropping precision. The angles between hot and cold spots, the way they cluster together, everything matches the inflationary playbook. It's as if the universe left us a receipt, proof of its own explosive growth spurt. And here's the kicker. Inflation doesn't just explain the past, it hints at a far stranger future. If space could expand that rapidly once, what's stopping it from happening again? Some theories suggest our universe might be just one bubble in an endless froth of inflating realities, each with its own laws of physics. The CMB's uniformity might be a clue that we're part of something vastly larger, a multiverse where inflation never truly stops. So when you stare at that grainy CMB map, remember, those subtle temperature differences aren't just data points. They're evidence of a universe that its own speed limit, a relic of a moment when reality itself rewrote the rules. And if inflation is real, it means our cosmos is far more dynamic and far more mysterious than we ever imagined. The cosmic microwave background doesn't just reveal the fingerprints of ordinary matter. It also carries the shadowy imprint of something far more mysterious: dark matter. Though invisible to telescopes, this enigmatic substance makes its presence known through gravity, bending the very fabric of the early universe like a weight pressing down on a mattress. When scientists analyzed the CMB's fluctuations, they found patterns that couldn't be explained by visible matter alone. The way galaxies cluster, the way light bends around cosmic voids, none of it adds up unless there's 5 times more matter than we can see. That missing mass, it's the universe's best-kept secret, a ghostly scaffold that holds everything together. Hear how dark matter left its mark. In the universe's first moments, ordinary matter, the stuff that makes up stars and planets, was tightly coupled with light, creating a tug-of-war between radiation's outward push and gravity's inward pull. But dark matter, unaffected by light, was free to clump together much earlier, forming gravitational wells that ordinary matter would later fall into. Those wells acted like invisible molds, shaping the distribution of hot and cold spots in the CMB. Without dark matter's gravitational pull, the universe's structure would look radically different. No grand galactic filaments, no sprawling clusters, just a faint, formless haze. The numbers are staggering. By measuring the CMB's subtle distortions, satellites revealed that dark matter makes up roughly 27% of the universe's total content. To put that in perspective, all the atoms in every star, planet, and speck of cosmic dust account for less than 5%. Dark matter is the silent architect, the unseen hand that sculpted the cosmos into the web we see today. And while we still don't know what it's made of, whether it's exotic particles or something even stranger, its gravitational signature is undeniable, etched into the CMB as clearly as ink on parchment. What's truly mind-bending is how dark matter's influence extends far beyond the ancient light. The same gravitational patterns seen in the CMB align perfectly with modern observations of galaxy rotation speeds and the bending of starlight around massive clusters. It's as if the universe left us 2 separate puzzles, one in the afterglow of the Big Bang, the other in the motions of today's galaxies, and they both point to the same invisible culprit. So when you look at a map of the cosmic microwave background, remember, those faint temperature variations aren't just relics of the past. They're a cosmic wanted poster, evidence of an elusive substance that outweighs everything we can see. And solving that mystery could rewrite our understanding of reality itself. If the cosmic microwave background were a detective's case file, dark energy would be the most baffling clue of all. An invisible force so powerful it's stretching the universe apart at an ever-increasing speed. Hear how we know it exists. When scientists measured the CMB's large-scale patterns, they discovered something startling. The universe isn't just expanding, that expansion is accelerating, like a car pressing harder on the gas pedal as it races down an endless highway. And the only explanation: a mysterious, repulsive force making up roughly 68% of the cosmos, dark energy. Think of the universe's total energy as a cosmic bank account. Ordinary matter, the stuff we can see, is like loose change, barely 5% of the balance. Dark matter is a hefty 27%, like a stack of bills. But dark energy, it's the majority shareholder, an overwhelming force that tilts the scales toward expansion. The CMB reveals this through its geometry. Because spacetime is flat, meaning parallel lines never converge, the universe's total mass-energy density must be perfectly balanced. But add up all the matter we've detected, and it's only about 1/3 of what's needed. That missing 2/3, that's dark energy's fingerprint. The smoking gun lies in the CMB's subtle distortions on the largest scales. Just as dark matter's gravity sculpted the early universe's clumps, dark energy left its mark by smoothing out certain fluctuations over vast distances. It's as if someone took an iron to the cosmos's wrinkles, but only in the stretches between superclusters. Satellites spotted this effect by comparing the CMB's temperature variations at different angular scales. The smaller bumps created by matter, the larger ones stretched by dark energy's push. What's truly unsettling is what this means for the universe's fate. If dark energy keeps strengthening, it could tear apart galaxies, then stars, even atoms, a scenario called the Big Rip. Or it might simply leave the cosmos a cold, empty void, all structure diluted into darkness. The CMB doesn't just tell us where we came from. It's a warning etched in ancient light, a message about how everything might end. Yet for all its power, dark energy remains a profound mystery. Is it the cosmological constant once imagined, an inherent property of space itself, or something far stranger, a force that evolves over time? The CMB's patterns hint at answers, but decoding them fully might require a new physics altogether. One thing's certain, this invisible driver, revealed by the universe's oldest light, holds the keys to our cosmic destiny. 13.8 billion years, that's the universe's birth certificate, etched into the cosmic microwave background with astonishing precision. How do we know this number isn't just an educated guess? Because the CMB acts like a cosmic hourglass, its grains of light falling in perfect rhythm with the expansion of space itself. When scientists measured the subtle patterns in this ancient glow, the spacing between hot and cold spots, the way light polarized as it traveled, they weren't just mapping temperature variations. They were reading a timeline, one that stretches back to the very first tick of the cosmic clock. Here, what's remarkable, this age isn't pulled from thin air. It's cross-checked by the universe itself. Take the oldest stars in our galaxy, ancient red giants whose ages we can estimate by their chemical composition. They clock in at around 13.4 billion years, close enough to the CMB's tally that it's like comparing two synchronized watches. Or consider the expansion rate of the universe, measured by observing distant supernovae. When you rewind that expansion like a film in reverse, everything converges to a single point, 13.8 billion years ago. The CMB doesn't just give us a number, it gives us a chorus of evidence, all singing the same cosmic birthday song. But how does light from the Big Bang's aftermath reveal time so precisely? It all comes down to the universe's expansion history. Imagine blowing up a balloon with tiny dots on its surface. As the balloon inflates, the dots move apart at a rate that depends on how fast you're blowing. The CMB's light is like those dots. Its wavelength has been stretched by the universe's expansion into microwaves, and the amount of that stretching tells us how long the balloon has been inflating. Factor in the density of matter, dark energy's push, and the universe's flat geometry, and the math points unequivocally to that magic number, 13.8 billion. What's even more profound is what this age implies. If the universe were significantly younger, we wouldn't have elements like carbon or iron, the building blocks of planets and life, because stars wouldn't have had time to forge them in their cores. If it were much older, the cosmos would be colder, darker, its stars long burned out. The CMB's timestamp isn't just a curiosity, it's a golden window, a span of time that allowed galaxies to form, stars to ignite, and life to emerge. And that's the real wonder. We're not just observers of this timeline. We're its product, stardust spun from a story 13.8 billion years in the making. Among the most puzzling absences in the universe is something that should be everywhere: magnetic monopoles. These hypothetical particles are the universe's missing puzzle pieces, predicted by grand unified theories to exist in staggering numbers. Unlike ordinary magnets, which always have a north and south pole, monopoles would carry just one, a solitary magnetic charge drifting through space. If these exotic particles formed in the early universe's unimaginable heat, as physics suggests they should, we'd be tripping over them today. Yet after decades of searching, from deep underground labs to cosmic ray detectors, not a single confirmed monopole has been found. This cosmic disappearing act is one of the strongest hints that our universe underwent something extraordinary in its first moments: cosmic inflation. Here, why? Without inflation, the dense, hot conditions of the early cosmos would have produced monopoles in such abundance that they'd outweigh all the stars in the universe. Their sheer mass would have warped space-time, bending galaxies into knots and leaving glaring imprints on the cosmic microwave background. But when we look at the CMB's near-perfect smoothness, there's no trace of this monopole mayhem. Inflation solves the mystery by suggesting the universe expanded so rapidly in its first fraction of a second that any monopoles formed were diluted to near non-existence, like a single grain of sand scattered across an endless desert. What's fascinating is how this ties the unimaginably small to the cosmically vast. Grand unified theories attempt to merge three of nature's fundamental forces, electromagnetism, and the strong and weak nuclear forces, into a single framework. These theories suggest that at energies high enough, like those in the early universe, these forces become indistinguishable. Monopoles are relics of that unification, cosmic fossils that should have survived to the present day. Their absence isn't just a curiosity, it's a smoking gun for inflation, a process so violent it stretched space-time thin enough to erase them from the observable cosmos. The implications go even deeper. If inflation didn't happen and monopoles were as common as theory predicts, the universe would look radically different. Galaxies might not have formed at all, their growth stunted by the gravitational pull of countless monopoles. The CMB's temperature variations would show wild fluctuations, like static on an old television. Instead, we see a calm, uniform glow, a silent witness to inflation's cleansing power. So the next time someone asks why we believe in cosmic inflation, point them to the monopoles that aren't there. Their absence is as telling as any visible clue, a blank space in the cosmic ledger that speaks volumes. It's a reminder that sometimes, what the universe hides is just as important as what it reveals. Even the most perfect cosmic blueprint has its quirks, and the cosmic microwave background is no exception. Hidden within its seemingly random fluctuations lies a strange alignment so baffling that scientists dubbed it the axis of evil. Picture this: if the universe is truly isotropic, meaning it looks the same in every direction, then the CMB's hot and cold spots should be scattered like a random splatter of paint. But when researchers mapped these variations, they found something unsettling, a peculiar preference in their orientation, as if the cosmos had quietly drawn a line through space and whispered, "This way is special." This isn't just a minor statistical glitch. The axis of evil, a name borrowed humorously from geopolitical jargon, defies one of cosmology's bedrock principles, the Copernican idea that we don't occupy a privileged place in the universe. If the CMB's fluctuations are aligned along some invisible axis, it suggests the cosmos might have a preferred direction, a cosmic north that challenges our assumptions about universal symmetry. Some theories propose this could be a shadow of something primordial, a structure or influence predating the Big Bang itself. Imagine finding fingerprints on a window, but the hand that left them existed before the glass was even made. What makes this mystery even thornier is how stubbornly it resists explanation. Could it be an artifact of our measurement techniques, a subtle bias in how we observe the CMB? Possibly, but multiple independent studies, including data from the satellite, have confirmed the anomaly. Others suggest it might hint at exotic physics, like the gravitational tug of a neighboring universe or a spacetime curvature we don't yet understand. Then there's the wildest idea of all, that the axis of evil is a cosmic fossil, a relic of a previous phase of the universe that collapsed and rebirthed itself in the Big Bang. For now, the axis of evil remains one of the CMB's greatest unsolved puzzles. It's a reminder that even our most precise maps of the universe still hold shadows at the edges, places where the rules we think we know might bend or break. And that's the thrill of cosmology. Every anomaly, every deviation, is a potential doorway to a deeper truth. So while the axis of evil might unsettle our models, it also invites us to look closer, to question harder, and to wonder what other secrets the universe has yet to reveal. Imagine drawing two perfectly straight lines on a sheet of paper. They'll never cross, never curve, never deviate from their parallel paths. Now scale that up to the entire universe, and you've got the mind-bending reality the cosmic microwave background has revealed. Our cosmos is geometrically flat. Not flat like a tabletop, but flat in the Einsteinian sense, where space-time itself has no intrinsic curvature. This isn't just a quirky detail. It's a cosmic tightrope act so precise that if the universe's expansion rate or density had deviated by even one part in a million billion during the Big Bang, everything would have either collapsed into a black hole or scattered into endless nothingness. The CMB is the ultimate witness to this balancing act. When scientists measured the angles between its temperature fluctuations, they found something extraordinary. Those patterns matched exactly what you'd expect if parallel light rays stayed parallel forever. In a curved universe like the surface of a globe, those angles would skew, with lines eventually converging or diverging. But the CMB's geometry is Euclidean, the same textbook math we learned in school. That flatness is a smoking gun, telling us the universe's total energy density sits at the exact tipping point between collapse and runaway expansion. Hear why this is so astonishing. For space-time to be flat today, the early universe had to be unimaginably fine-tuned. Picture a pencil balanced perfectly on its tip, any slight nudge, and it topples. The cosmos faced the same razor's edge scenario. Matter and energy's gravitational pull had to counterbalance the outward thrust of expansion with near-perfect precision. Too much matter, and gravity would have crumpled the universe into a big crunch. Too little, and everything would have flown apart so fast that galaxies could never form. The CMB's flatness is the universe's way of showing us it got the recipe exactly right. But how? Cosmic inflation provides the answer. That explosive early growth spurt didn't just stretch the universe. It ironed out any curvature like a cosmic steamroller, leaving space-time so flat that even 13.8 billion years of expansion haven't curved it. The CMB's geometry is inflation's autograph, a signature of that brief but transformative moment when the universe reset its own shape. What's even wilder is what this means for the cosmos's total energy. In its equations, flatness implies that the universe's energy density, the combined contribution of matter, and dark energy, must equal a critical value. The CMB doesn't just confirm this, it lets us weigh each component like ingredients in a cosmic cake. Ordinary matter and dark matter provide the gravitational glue, while dark energy fuels the expansion. Their sum. Precisely enough to keep the universe balanced on that knife edge of flatness. So the next time you hear the universe is flat, don't think of a pancake. Think of a high-wire act spanning billions of light years, with the CMB as the safety net proving the performer never faltered. It's a clue etched in ancient light, revealing just how narrowly we escaped cosmic catastrophe. And that precision, it's either the luckiest roll of the dice, or a hint that there's more to the story than we've yet uncovered. The universe wasn't always filled with stars and galaxies. It began as a searing plasma, so hot that atoms couldn't hold together. Electrons zipped freely through a roiling soup of particles, scattering light like fog in a storm. But then, around 380,000 years after the Big Bang, something extraordinary happened. The cosmos cooled just enough for electrons and protons to finally link up, forming the very first atoms, neutral hydrogen. This moment, called recombination, didn't just create matter as we know it. It cleared the cosmic fog, allowing light to travel freely for the first time. The photons released in that instant have been journeying across space ever since, stretched by expansion into the microwave glow we call the cosmic microwave background. But the CMB isn't just a relic of that transformative era, it's a detailed ledger of how those first atoms came to be. When light broke free during recombination, it carried with it a unique signature: polarization. Imagine sunlight reflecting off a lake, its waves aligned in a specific direction. Similarly, the CMB's light was polarized by its last interactions with electrons, leaving behind subtle patterns that act like cosmic breadcrumbs. By studying these patterns, scientists can reconstruct the precise conditions of the universe's chemical infancy, down to the density of hydrogen atoms per cubic meter and the exact temperature at which they formed. What's astonishing is how much this tells us. The polarization data reveals that recombination wasn't instantaneous. It unfolded over tens of thousands of years, a gradual process where electrons and protons danced closer and closer until they finally bonded. The CMB's polarization maps, like those from the satellite, even show how this process varied across space, with some regions forming atoms slightly faster than others. These minute differences are critical because they sowed the seeds for the universe's first structures. Where hydrogen clumped together just a bit more densely, gravity eventually pulled in more matter, creating the scaffolding for galaxies. Here, where it gets even more profound, the way light polarized during recombination also depends on the universe's geometry and content. If dark matter hadn't been present, for example, electrons would have moved differently, leaving a distinct imprint on the CMB's polarization. The fact that we see the patterns we do is yet another confirmation that dark matter shaped the cosmos from its earliest moments. Similarly, the absence of certain polarization rules out alternative theories about the universe's composition, like exotic particles or extra dimensions. So when you look at a map of the CMB's polarization, you're not just seeing ancient light. You're witnessing the universe's first chemistry experiment, the moment it transitioned from a chaotic plasma to a place where atoms and eventually stars and life could exist. It's a snapshot of creation itself, frozen in time and waiting for us to decode its secrets. The cosmic microwave background might steal the spotlight, but there's another whisper from the Big Bang hiding in plain sight. A ghostly sea of neutrinos so vast it outnumbers every atom in the universe by 1,000,000,000 to 1. These aren't just any particles. They're relics from the first second of creation, racing through space at nearly the speed of light, barely interacting with matter as they pass through entire planets like they're not even there. Yet despite their elusiveness, these cosmic neutrinos left their fingerprints on the CMB, subtly shaping its fluctuations in ways that reveal secrets about the universe's fiery infancy. Hear how it works. In the universe's first moments, neutrinos were born in staggering numbers, so energetic they dominated the cosmos alongside light. But unlike photons, which slammed into electrons and protons, neutrinos barely noticed matter. They slipped through the dense plasma like ghosts through walls. This indifference gave them a head start, streaming outward ahead of the light that would later become the CMB. As they raced away, their sheer numbers and energy tugged at the fabric of the early universe, gravitationally nudging matter into slightly different patterns. When light finally broke free 380,000 years later, it carried the imprint of those neutrino-driven tweaks, tiny shifts in the distribution of hot and cold spots that wouldn't exist without them. What's astonishing is how much these invisible particles reveal. By analyzing the CMB's fine-scale fluctuations, scientists can actually count the cosmic neutrino background, confirming there are around 300 of these particles per cubic centimeter, a fossilized echo of the Big Bang's first second. Even more mind-bending, the CMB lets us weigh them. Neutrinos were long thought to be massless, but the way they smeared out certain small-scale patterns in the CMB proved they must have at least a whisper of heft, about 1/1,000,000th the mass of an electron. That might sound negligible, but in a universe teeming with neutrinos, their combined gravity helps sculpt the large-scale structure of everything we see. The implications go even deeper. Neutrinos move so fast they act like cosmic grease, smoothing out small clumps of matter that might otherwise have grown into galaxies. This explains why the CMB shows fewer tiny fluctuations than expected. Neutrinos literally ironed out the universe's wrinkles on the smallest scales. And because they decoupled from matter so early, they offer a snapshot of conditions even before recombination, a window into the universe's hyperactive toddler phase. So while the CMB's light gets all the attention, its silent partner, the cosmic neutrino background, is just as crucial. Together, they form a stereo recording of the Big Bang, one channel capturing light's last scatter, the other preserving the universe's faintest, fastest ghosts. And decoding their duet might hold the key to physics beyond our wildest theories, from the nature of dark matter to the possibility of extra dimensions. The universe didn't just leave us one afterglow, it left us two. And we're only beginning to listen. One of the most daring ideas lurking in the cosmic microwave background's shadowy corners is the possibility that our universe isn't alone. Scattered across the CMB's tapestry are peculiar anomalies, regions so statistically unlikely they've made scientists question everything. Take the so-called cold spot, a chilling void spanning nearly 2 billion light-years where temperatures dip mysteriously lower than anywhere else. Statistically, such a feature should only appear once in every 50 universes. Yet there it sits, an icy bruise on the sky, defying easy explanation. This is where the multiverse hypothesis crashes onto the scene. Imagine the early cosmos not as a single expanding fireball, but as a froth of bubble universes, each inflating at its own pace, governed by its own laws. In this chaotic sea, bubbles might occasionally collide, leaving scars on one another's surfaces. The cold spot could be one such scar, a cosmic dent from a long-ago encounter with another universe brushing against ours. It's a wild idea, but the math holds up. Simulations show that a collision with a neighboring bubble would create precisely the kind of temperature dip and polarization patterns we observe. What's fascinating is how the CMB keeps this radical theory alive. If the cold spot were the only anomaly, we might dismiss it as a fluke. But other quirks, like large-scale asymmetries in temperature distribution or unexpected alignments of fluctuations, also resist conventional explanations. Together, they form a constellation of oddities that, while inconclusive, nudge us toward considering possibilities beyond our single universe. Even the CMB's overall smoothness, long hailed as evidence for inflation, might have a multiverse twist. Inflation could be endless, spawning infinite bubbles beyond our cosmic horizon, each with its own unique physics. Our observable universe would just be one quiet neighborhood in an unimaginably vast metropolis. Of course, skepticism is warranted. The multiverse remains untestable by traditional standards. You can't peer beyond the edge of spacetime to snap a photo of another bubble. But the CMB offers indirect clues, a forensic trail that might one day lead to firmer ground. For now, these anomalies are cosmic riddles, reminding us that the universe's deepest truths often hide in its most unexpected corners. Whether they're glimpses of a grander multiverse or mere statistical noise, one thing's certain: the CMB still has stories left to tell, and some of them might rewrite reality as we know it. Theory of general relativity tells us gravity isn't a force reaching across space, it's the bending of spacetime itself, a warp moving at the speed of light. But what if that speed isn't constant? What if gravity's influence ripples through the cosmos just a fraction faster or slower than we've assumed? That's where the cosmic microwave background becomes our ultimate testing ground. Hidden within its ancient light are subtle clues about how gravity's speed shaped the universe's largest structures, offering a rare chance to put century-old ideas on trial. Here, how it works. In the early universe, gravity's pull had to compete with the outward rush of cosmic expansion. If gravity propagated even slightly slower than light, its influence would lag behind, leaving weaker imprints on the CMB's temperature fluctuations. Imagine trying to mold clay as it's being stretched. If your fingers can't keep up, the shapes you create will be fainter, less defined. That's precisely what scientists look for in the CMB's patterns, the ghostly signature of gravity struggling to sculpt matter against the tide of inflation. So far, the data aligns perfectly with general relativity's prediction. Gravity moves at light speed, no more, no less. But the tiniest deviation would send shockwaves through physics, hinting at hidden dimensions, exotic particles, or even flaws in its framework. The stakes couldn't be higher. If gravity's speed varied, even by a minuscule amount, it would rewrite our understanding of black holes, gravitational waves, and the universe's expansion history. The CMB acts like a cosmic speed trap, catching gravity in the act as it shaped galaxy clusters and cosmic voids. By comparing the distribution of these structures with theoretical models, researchers can measure gravity's influence with unprecedented precision. It's as if the universe left us a stopwatch embedded in its oldest light, ticking in perfect sync with relativity's predictions, for now. But the hunt isn't over. Future telescopes, like the upcoming LightBird satellite, will scrutinize the CMB's polarization for even fainter traces of gravitational anomalies. The tiniest discrepancy could crack open the door to new physics, revealing forces or fields beyond imagination. So while the CMB has so far confirmed gravity's speed with resounding certainty, its true power lies in the questions it keeps asking. In the silent glow of microwaves, the universe whispers its deepest mysteries, and gravity's rhythm might hold the key. One of the greatest unsolved puzzles of cosmology isn't about what's in the universe, it's about what is. According to everything we know, the Big Bang should have created equal amounts of matter and antimatter, particles and their mirror opposites that annihilate on contact. Yet today, antimatter is vanishingly rare, while matter dominates everything from stars to smartphones. This cosmic imbalance, called baryon asymmetry, is written plainly in the cosmic microwave background, and its fingerprints point to a violent betrayal in the universe's first moments. The CMB reveals this mystery through its exquisitely precise accounting of protons and neutrons. By measuring how propagated in the early universe's plasma, scientists can calculate the exact density of ordinary matter, the so-called baryon density, with an accuracy of just 1%. That number is shockingly small. For every billion photons in the CMB, there are only about 6 baryons. But here's the catch. If matter and antimatter had been perfectly balanced at the Big Bang, those 6 baryons would have met 6 antibaryons, annihilating into pure energy and leaving behind a barren, particle-free cosmos. The fact that we exist at all means something tipped the scales. The leading theory involves a process called, where hypothetical heavy neutrinos decayed unevenly in the universe's first trillionth of a second, producing slightly more matter than antimatter. The CMB supports this idea in 2 ways. First, its measured baryon density aligns with predictions from particle physics about how much excess matter could survive such an imbalance. Second, the CMB's polarization patterns rule out alternative explanations, like antimatter-dominated regions hiding beyond our cosmic horizon. If such regions existed, their annihilation borders would have left glaring scars in the CMB's smoothness, scars we simply don't see. But the real smoking gun lies in the CMB's acoustic peaks. The way baryons interacted with photons in the early universe left a distinct signature in these oscillations, like a musician's unique vibrato. By analyzing these peaks, researchers confirmed that ordinary matter, protons and neutrons, makes up about 4.9% of the universe's total energy budget. That number might seem insignificant, but it's the residue of an ancient cataclysm, the leftover crumbs from a near-total annihilation where matter won by the slimmest margin. Just one extra particle in every 10 billion. What's haunting is how fine-tuned this imbalance had to be. If the excess had been slightly smaller, gravity wouldn't have had enough material to clump into galaxies. Slightly larger, and the universe would have collapsed into black holes long before life could emerge. The CMB doesn't just tell us the universe preferred matter, it tells us that preference was calibrated to a precision that defies chance. Whether that's a clue to deeper physics or pure cosmic luck remains one of the greatest open questions in science. But one thing's certain, without that fragile asymmetry, the cosmos would be a silent, lightless void, and we wouldn't be here to ponder it. The cosmic microwave background gives us a precise measurement of how fast the universe is expanding, or at least it should. According to the CMB's detailed fluctuations, the cosmos is stretching at about 67 kilometers per second for every of space, a number derived from the way dark energy and matter sculpted those ancient ripples. But here, the problem. When astronomers measure the expansion rate using nearby stars and galaxies, they get a different answer, around 73. That gap might seem small, but in cosmology, it's a chasm. This disagreement, known as the tension, isn't just a rounding error. It's a full-blown crisis, forcing scientists to question whether we've misunderstood the universe's ingredients, its history, or even the laws of physics themselves. The stakes couldn't be higher. The CMB's expansion rate comes from extrapolating backward, using the universe's composition, dark energy, dark matter, and ordinary matter, as a recipe to calculate how quickly space should be stretching today. Meanwhile, local measurements rely on observing pulsating stars called Cepheids and exploding supernovae, which act like cosmic yardsticks. These two methods should agree, like two clocks ticking in sync. The fact that they don't suggests one of them is broken, or worse, that our fundamental assumptions about reality are flawed. Some theorists argue the tension could mean dark energy isn't constant, but evolves over time, growing stronger or weaker in ways we haven't accounted for. Others propose exotic new particles, like dark radiation, that might have subtly altered the early universe's expansion. Then there's the radical idea that we're living in a cosmic void, a bubble of space that skews our local measurements. But each of these fixes comes with its own problems. Tweak one parameter to resolve the tension, and you risk throwing off other exquisitely precise CMB predictions. What makes this puzzle so thrilling is that the CMB isn't just the source of the tension. It's also our best tool for solving it. Future missions, like the European Space Agency's Euclid telescope, will map the universe's large-scale structure with unprecedented detail, searching for clues in the way galaxies cluster. Meanwhile, gravitational wave observations could provide an entirely independent way to measure cosmic expansion, acting as a tiebreaker. For now, the tension remains one of cosmology's most tantalizing mysteries. It's a reminder that even our most trusted cosmic maps might still hold uncharted territories, places where the rules we take for granted bend or break. Whether the solution lies in new physics, hidden errors, or something even stranger, one thing's certain: the CMB isn't just a relic of the past. It's a living puzzle, challenging us to rethink everything we know about the universe's grand story. Magnetic fields are everywhere in the cosmos today, woven through galaxies, wrapped around stars, even threading the empty voids between them. But where did these invisible force lines come from? The answer might be hiding in the cosmic microwave background, imprinted in the delicate swirls of its polarized light. Some theories propose that the infant universe wasn't just a searing soup of particles. It crackled with primordial magnetic fields, powerful enough to shape the destiny of matter itself. If these ancient fields exist, their ghostly fingerprints could linger in the CMB's polarization. a subtle twisting of light that would rewrite our understanding of cosmic magnetism's origins. Here, why this matters. Magnetism isn't just a cosmic afterthought. It sculpts gas into galaxies, channels star-forming material, and even influences how black holes feed. But today's magnetic fields are messy patchworks, tangled by billions of years of stellar winds and supernova explosions. To find their true source, we need to peer back to a time before the first stars, when the universe was still a blank canvas. That's where the CMB becomes a detective's tool. When light scattered off electrons in the early universe, any primordial magnetic fields would have left a telltale twist in its polarization, a spiral pattern called B modes. Unlike the E modes created by density fluctuations, B modes are the cosmic equivalent of a fingerprint's whorls, betraying the presence of twisting, dynamic forces at play. The hunt for these signals is already. Telescopes like the South Pole Telescope and the Cosmology Telescope scan the CMB's polarization with exquisite sensitivity, searching for the faintest swirls that might betray these ancient fields. If they're found, the implications would be staggering. Primordial magnetism could mean the universe was born with its own built-in wiring, a fundamental property as intrinsic as space-time itself. Some models even suggest these fields could have acted as cosmic scaffolding, guiding the collapse of matter into the first galaxies long before gravity alone could do the job. Yet the mystery deepens when we ask how such fields could have arisen in the first place. One tantalizing idea ties them to cosmic inflation, that same explosive expansion that smoothed the early universe. Quantum fluctuations during inflation might have generated electromagnetic turbulence, stretching microscopic magnetic fields to cosmic proportions in less than a blink. Alternatively, phase transitions in the early universe's seething plasma could have spawned magnetism like frost crystallizing on a window, a spontaneous order emerging from chaos. For now, the CMB keeps its secrets close. But with every new polarization map, we edge closer to answering whether magnetism is a latecomer to the cosmic story or a hidden architect, shaping the universe from its very first moments. The tiniest ripples in the cosmic microwave background might hold the biggest surprise of all, proof that the universe itself was born from quantum uncertainty. Picture this: in the first incomprehensibly small fraction of a second after the Big Bang, the cosmos wasn't just hot and dense. It was a seething quantum foam, where particles flickered in and out of existence faster than light could cross an atom. According to quantum mechanics, empty space isn't truly empty. It's a bubbling cauldron of virtual particles, constantly appearing and vanishing like bubbles in a boiling pot. Normally, these quantum jitters are too small to matter on cosmic scales. But inflation, that explosive early expansion, acted like a cosmic magnifying glass, stretching those subatomic tremors to the size of galaxies. What's astonishing is how perfectly this explains the CMB's patterns. Those microscopic quantum fluctuations, once amplified by inflation, became the seeds of all cosmic structure. Imagine blowing up a microscopic dust speck to the size of a mountain. Every tiny irregularity becomes a valley or peak. Similarly, the quantum ripples became the hot and cold spots we see in the CMB, the blueprint for everything from star clusters to. The math is eerily precise. When scientists calculate how quantum fluctuations should stretch across an inflating universe, the predicted pattern matches the CMB's temperature variations down to the tiniest detail. It's as if we've found the universe's quantum fingerprint, smeared across the sky. This connection between the unimaginably small and the cosmically vast is more than just a neat theory. It's a bridge between two seemingly disconnected realms of physics. Quantum mechanics governs the behavior of particles smaller than atoms, while general relativity describes the warping of spacetime by massive objects like stars and black holes. For decades, these two theories have refused to play nice, creating one of science's greatest unsolved problems. But the CMB offers a rare glimpse of their intersection, showing how quantum effects writ large shape the entire cosmos. Here, where it gets even wilder. Some theories suggest these quantum ripples didn't just sculpt matter. They might have also spawned gravitational waves, ripples in spacetime itself. If so, future telescopes could detect their faint imprint in the CMB's polarization, opening a window into the universe's very first instance. We might even find clues about quantum gravity, the holy grail of physics, hidden in those ancient microwaves. So the next time you hear about the CMB's fluctuations, remember, you're not just looking at temperature variations. You're seeing quantum mechanics painted across the cosmos, a reminder that the universe's grandest structures grew from the tiniest tremors of nothingness. And that's perhaps the most humbling insight of all. Our vast, majestic universe might owe its existence to the faintest whisper of quantum uncertainty. One of the strangest mysteries lurking in the cosmic microwave background isn't just about temperature or light, it's about motion. Scientists have noticed something bizarre. Thousands of galaxy clusters aren't just drifting randomly through space. Instead, they seem to be streaming in the same direction at staggering speeds, as if pulled by some invisible cosmic current. This eerie phenomenon, dubbed the dark flow, defies everything we know about how the universe should behave. After all, the Big Bang's afterglow suggests matter should be scattered evenly in all directions, with no preferred axis of movement. So why are these galaxies racing toward a single point beyond the edge of our observable universe? The first clue lies in the CMB's dipole anisotropy, a subtle temperature difference between opposite sides of the sky. Normally, this variation is explained by our solar system's motion relative to the CMB's rest frame. But when astronomers subtracted that expected motion, they found a residual signal, galaxy clusters moving faster and more uniformly than local physics can account for. It's as if the universe's largest structures are caught in a gravitational undertow, tugged by something so massive it warps space itself, yet lies entirely outside our cosmic horizon. What could possibly exert such a pull? One radical theory suggests the dark flow might be evidence of a neighboring universe, a separate bubble of reality brushing against our own in the greater multiverse. Inflation, the process that stretched our universe to its vast size, could have spawned countless other universes, each with its own physical laws. If one of these sibling universes happened to form close enough, its gravitational influence might seep through the cosmic veil, tugging our galaxies toward it like a magnet. Alternatively, the flow could trace back to colossal structures from the early universe, cosmic defects, left over from phase transitions in the first fractions of a second, relics so dense they bend spacetime on unimaginable scales. Skeptics argue the dark flow might simply be a measurement error or an artifact of incomplete data. But multiple independent studies, including analyses of X-ray clusters and the CMB's kinematic effect, continue to detect this mysterious motion. The latest observations even suggest the flow extends billions of light-years farther than initially thought, deepening the enigma. If the dark flow is real, it rewrites our understanding of cosmic boundaries. The observable universe, the portion we can see, might just be a tiny island in a far vaster ocean with currents flowing toward shores we'll never glimpse. It's a humbling reminder that for all we've decoded in the CMB, the cosmos still holds secrets that defy explanation, secrets written not in light, but in the silent, relentless drift of galaxies toward the unknown. For billions of years after recombination, the universe was a vast, silent sea of darkness. No stars, no galaxies, just a thin fog of hydrogen gas stretching endlessly in every direction. This was the cosmic dark age, an era so devoid of light that if you'd been there, your eyes would have seen nothing but infinite black. Then, somewhere around 200 million years after the Big Bang, something extraordinary happened. The first stars flickered to life, their brilliant ultraviolet rays piercing the gloom like matchsticks struck in a cavern. This moment, the cosmic dawn, didn't just illuminate the universe. It fundamentally transformed it, blasting apart neutral hydrogen atoms and flooding space with free electrons once more. And though those first stars vanished long ago, their legacy lives on in the cosmic microwave background, etched into its polarized light like a fossilized sunrise. The key to unraveling this epoch lies in a process called. When those first massive stars ignited, their intense UV radiation was powerful enough to strip electrons from surrounding hydrogen atoms, the gas that had been neutral since recombination. Think of it like a frost-covered window suddenly hit by sunlight. The icy crystals don't just melt, they sublimate directly into vapor. Similarly, didn't just light up the universe. It rewired its very structure, tearing apart the atomic fabric that had persisted for eons. But here's the astonishing part. As those freed electrons scattered the CMB's photons one last time, they imprinted a unique signature on the light's polarization, a ghostly echo of the moment the cosmos woke up. Satellites-like and ground-based observatories have spent years hunting for this signal. The telltale clue, a distinctive swirling pattern in the CMB's polarization known as B modes, created when free electrons interacted with the ancient light. It's as if the universe left us a time-stamped receipt for its own awakening, a record of when the lights first came on. By measuring these patterns, scientists have pinned the peak to roughly 500 million years after the Big Bang, though the first stars likely began flickering even earlier, like distant campfires in a slowly brightening wilderness. What's truly mind-bending is how much this reveals about those elusive first stars. Unlike modern stars, which are often smaller and richer in heavier elements, the pioneers of the cosmic dawn were behemoths, hundreds of times more massive than our sun, burning ferociously bright and dying young in spectacular supernovae. Their explosive death seeded the universe with the first heavy elements, forging the raw materials for planets, life, and eventually us. The CMB's polarization doesn't just mark when happened. It hints at how quickly those stars arose, how fiercely they shone, and how thoroughly they reshaped the cosmos. Yet mysteries remain. The CMB suggests was a drawn-out process spanning hundreds of millions of years, but was it a smooth transition, like a dimmer switch slowly turning up, or a chaotic fireworks display of sporadic stellar ignition? Future telescopes, like the James Space Telescope, aim to spy directly on this epoch, hunting for the faint glow of those first galaxies. But for now, the CMB remains our most powerful time machine, its polarized whispers carrying stories of an era when darkness gave way to light, and the universe as we know it truly began. The cosmic microwave background isn't just a map of space. It's a clock, ticking with such perfect synchrony across the cosmos that it reveals something profound about time itself. Everywhere we look, the CMB's temperature fluctuations are nearly identical, varying by less than 1 part in 100,000. This staggering uniformity isn't just about heat. It's a testament to time's unwavering flow, a cosmic metronome that's been ticking in lockstep since the universe's infancy. Imagine standing in a vast field where every blade of grass grew at exactly the same rate, bending in the same breeze, aging in perfect unison. That's the universe we live in, a place where time isn't just a local phenomenon, but a thread woven seamlessly through the fabric of reality. This isotropy, the sameness in all directions, isn't just a curious detail. It's the foundation of modern cosmology, the reason we can speak of a single universal now. Without it, the cosmos would be a patchwork of disjointed timelines, some regions aging faster, others slower, like a shattered mirror reflecting fractured realities. The CMB's consistency tells us that time, much like space, was forged in the Big Bang's crucible with a coherence that's held firm for 13.8 billion years. Even as galaxies race apart, Even as black holes warp spacetime into knots, the underlying rhythm of time remains unbroken, a beat that pulses through every corner of the observable universe. How do we know this isn't just an illusion? Because the CMB's light is the ultimate timekeeper. Photons emitted during recombination have been traveling toward us for nearly the universe's entire history, their wavelength stretched by expansion but their underlying physics unchanged. If time flowed unevenly, if some regions of space experienced it faster or slower, those photons would bear the scars, their energies skewed in ways we'd easily detect. Instead, they arrive with near-perfect uniformity, a chorus of ancient voices all singing the same tune. It's as if the universe handed us a stopwatch at the moment of its birth, and every measurement since has confirmed. Time marches onward everywhere as one. This cosmic synchronicity isn't just poetic. It's a razor-sharp test for theories that dare to challenge vision. Alternate models of gravity or exotic physics predicting time's variability crumple under the CMB's relentless consistency. Even the wildest ideas, like certain multiverse scenarios where neighboring bubbles of reality might tick to different clocks, must contend with the fact that our observable universe shows no cracks in time's facade. The CMB doesn't just support the idea of a unified timeline, it demands it, ruling out whole classes of theories that can't explain its flawless isotropy. Yet the deepest mystery isn't that time flows uniformly, it's why. Inflation, the universe's explosive early growth spurt, likely ironed out any initial irregularities, stretching quantum fluctuations into cosmic-scale smoothness. But that only pushes the question back. What set inflation's clock, ensuring it started and stopped with such precision across all of space? The CMB offers no easy answers, only whispers of a deeper order, a symmetry so fundamental it might lie beyond spacetime itself. For now, we're left with a humbling truth. The universe doesn't just have a history. It has a heartbeat, steady and universal, echoing through the oldest light we can see. Computer simulations of the universe have a problem. They predict thousands of small satellite galaxies orbiting large ones like our Milky Way, but when we look up at the night sky, we only find a handful. This mismatch, known as the missing satellites problem, has puzzled astronomers for decades. But here, where the cosmic microwave background steps in as an unlikely detective. The CMB's detailed map of dark matter's gravitational influence might hold the key to why these tiny galaxies never formed, or why they're hiding in plain sight. The answer lies in the peculiar behavior of dark matter. In supercomputer simulations, dark matter clumps together under gravity, creating countless dense pockets called halos. These halos should have attracted enough gas to ignite stars, birthing swarms of dwarf galaxies. But reality tells a different story. Our telescopes spot only a fraction of what the models predict. The CMB helps solve this riddle by revealing how dark matter interacts with itself and ordinary matter. Those subtle temperature fluctuations in the ancient light show dark matter's gravitational pull sculpted the early universe with surgical precision, but not in the way simulations assumed. One compelling theory suggests dark matter might be colder than we thought, not in temperature, but in how sluggishly its particles moved in the early cosmos. Cold dark matter would clump easily, forming those excessive halos in simulations. But if dark matter had even a tiny amount of warmth, meaning its particles zipped around faster, it would have smeared out the smallest clumps, preventing them from growing into galaxies. The CMB's large-scale structure supports this idea, showing dark matter's fingerprints align better with slightly warmer models. Another possibility is even stranger. Dark matter might interact with itself through unknown forces, like invisible versions of electromagnetism. These interactions could have smoothed out small-scale clumps, erasing potential dwarf galaxies before they could form. The CMB's polarization patterns hint at this scenario, with certain anomalies in how dark matter's gravity lends the ancient light. It's as if dark matter didn't just passively shape the cosmos. It actively pruned its own growth, leaving gaps where galaxies should have been. Yet some scientists argue the satellites aren't missing at all, they're just too faint to see. The smallest galaxies might have formed but burned through their gas too quickly, leaving behind dark, starless husks invisible to our telescopes. The CMB's insights into support this, suggesting the first stars' intense radiation could have sterilized nearby dwarf galaxies, stripping away their star-forming fuel. Whatever the truth, the missing satellites problem isn't just about counting galaxies. It's a stress test for our understanding of dark matter's nature. The CMB doesn't just illuminate the universe's past, it forces us to question whether we've imagined dark matter all wrong. Are its particles heavier or lighter than we assumed? Do they collide, decay, or hide in extra dimensions? Every undiscovered dwarf galaxy is a silent witness, and the CMB holds the decoder ring. So while simulations and observations clash, the cosmic microwave background offers a middle ground, a way to peer into dark matter's rulebook and rewrite the story of galactic evolution. The missing satellites aren't a flaw in the cosmos, they're clues waiting for us to decipher their hidden language. At the heart of nearly every galaxy, including our own Milky Way, lurks a supermassive black hole, a gravitational monster weighing millions or even billions of times more than our Sun. But here's the puzzle. Some of these cosmic giants existed when the universe was less than 1 billion years old, far too young to have grown so large by conventional means. It's like finding a skyscraper in the middle of an ancient wilderness, with no logical explanation for how it got there. The cosmic microwave background might hold the answer, its subtle density fluctuations preserving clues about how these black holes could have sprouted from mere seeds into behemoths almost overnight. The mystery begins with timing. Black holes typically grow by slowly devouring gas and stars over billions of years, but the ones we've spotted in the early universe didn't have that luxury. They were already fully formed when the cosmos was just a toddler, suggesting they started life with a massive head start. One leading theory proposes these black holes were born not from dying stars, but from the direct collapse of enormous gas clouds in the universe's first 100 million years. These clouds, denser than anything in the modern cosmos, could have bypassed the star-forming stage entirely, collapsing straight into black holes with masses thousands of times that of our Sun. The CMB's density variations act like a cosmic fossil record, showing where these ultra-dense pockets of matter might have formed. But how do we connect those ancient fluctuations to black holes? It's all about gravity's snowball effect. Regions of slightly higher density in the early universe, imprinted in the CMB, attracted more matter over time, growing denser and hotter until they reached a tipping point. In the most extreme cases, these regions might have birthed direct collapse black holes, objects so massive from birth that they could rapidly gorge on surrounding gas, reaching supermassive status in a cosmic blink. The CMB's temperature variations serve as a treasure map, highlighting where these rare, ultra-dense environments likely existed. There's another twist. Some models suggest these early black holes didn't just grow, they merged. Like raindrops pooling into puddles, smaller black holes could have combined in the dense early universe, creating giants far faster than any single seed could manage on its own. The CMB's large-scale structure supports this idea, with certain clustering patterns hinting at an era of violent black hole collisions. It's a cosmic game of Pac-Man, where the biggest eaters grew fastest, their gravitational influence warping the distribution of matter in ways we can still detect today. Yet the most tantalizing possibility is that these black holes didn't just shape galaxies, they them. Their ferocious energy output might have heated surrounding gas, preventing it from cooling into stars too quickly and regulating the growth of entire galaxies. The CMB's polarization patterns, which record how light scattered off electrons during show signs of this early feedback, as if the universe's first black holes were cosmic architects, carving out the voids and filaments we see today. So while supermassive black holes remain among the universe's most enigmatic objects, the CMB offers a backstage pass to their origins. Those faint temperature fluctuations aren't just relics of density variations. They're the birth certificates of the cosmos's most powerful monsters, written in the language of gravity and light. And as we decode them, we're not just solving a black hole mystery. We're uncovering the violent, chaotic processes that shape the universe as we know it. The cosmic microwave background doesn't just tell us where the universe came from, it whispers where it's going. Woven into those ancient photons is a prophecy, written in the language of dark energy and expansion. The verdict: the cosmos isn't just growing, it's accelerating toward a fate so desolate it makes black holes seem warm by comparison. Scientists call it the heat death, a slow, inexorable unraveling where galaxies drift apart like ships in an ever-widening sea. Stars burn out one by one, and space itself stretches into an endless, frozen void. And the CMB is the smoking gun, its patterns revealing dark energy's grip tightening with every passing eon. Here, how we know. The same subtle distortions in the CMB that measure the universe's flatness also tally its energy budget, the balance between matter's gravitational pull and dark energy's repulsive push. That balance is tipping. Dark energy, making up roughly 68% of the cosmos, isn't just winning, it's rigging the game. Unlike matter, whose influence weakens as the universe expands, dark energy's strength appears constant, or worse, growing. That means every new cubic meter of space adds more push to the cosmic accelerator, driving galaxies apart faster and faster. The CMB's large-scale fluctuations, those faint smudges where gravity once struggled against expansion, are fossilized evidence of this losing battle. But what does this mean for the far future? Picture a universe where the expansion rate outpaces even light's ability to bridge the gaps. First, distant galaxies will vanish over the horizon, their light stretched into invisibility. Then galactic clusters will isolate, their stars burning through fuel with no new generations to replace them. Eventually, even atoms themselves may decay, their protons, once thought immortal, crumbling into radiation over unfathomable timescales. The CMB, that afterglow of creation, will fade too, its photons stretched into wavelengths so long they'll dissolve into the background noise of space itself. Yet the CMB holds a paradox. While it spells doom for the cosmos at large, it also reveals how finely tuned our current era is for life. Those same dark energy fluctuations that doom the future also ensured the universe didn't collapse too soon or rip apart too quickly. Stars had time to forge heavy elements, planets to coalesce, and life to emerge. In that sense, the CMB isn't just a relic of the past or a prophecy of the future. It's a mirror, reflecting the fleeting, fragile moment we occupy. A sliver of cosmic time when the universe was neither too chaotic nor too barren, but just right for stories like ours to unfold. So while the heat death may be inevitable, it's also unimaginably distant, a trillion years hence. For now, the CMB's whispers remind us that endings are woven into beginnings, and that even in a universe destined for cold silence, the present crackles with warmth and wonder. The cosmos gave us light, time, and a front row seat to its grandest acts. However it ends, the show's not over yet. The cosmic microwave background is more than just a faded glow from the universe's infancy. It's the ultimate cold case file, packed with clues that rewrite everything we thought we knew about reality. Think of it as the universe's autobiography, written not in ink but in microwaves, each fluctuation a sentence revealing hidden chapters about dark matter's gravitational grip, dark energy's relentless push, and even whispers of other universes brushing against our own. What started as static on a radio telescope in 1965 has become humanity's most powerful time machine, peeling back layers of cosmic history like an archaeologist deciphering ancient hieroglyphs. But here's what's truly astonishing. We've only scratched the surface. The CMB's full story is still coming into focus, with next-generation telescopes like the Observatory and Lightbird poised to study its polarization with unprecedented precision. These missions could uncover evidence of primordial gravitational waves, ripples in spacetime from inflation's violent birth pangs, or spot anomalies that hint at physics beyond theories. Imagine decoding a message where every new line changes how we read the ones before it. That's the CMB's promise, a living document constantly offering fresh revelations as our tools evolve. And the implications stretch far beyond astronomy. The CMB's clues have already reshaped philosophy, forcing us to grapple with questions that sound straight out of science fiction. Are we one universe among infinite others? Was time even linear before the Big Bang? The answers might lie in those microwave patterns, waiting for the right combination of math and imagination to unlock them. It's humbling to realize that the same light bathing our planet from all directions connects us to the cosmos's first moments, and to futures so distant they defy comprehension. So as you step outside tonight and glance up at the stars, remember this: you're not just looking at space. You're seeing the aftermath of a primordial fireball, its secrets mapped in faint microwaves that have traveled for over 13 billion years to reach you. The cosmic microwave background isn't just a relic. It's an invitation to keep exploring, questioning, and marveling at the fact that we, tiny, fleeting creatures on a pale blue dot, can read the universe's deepest secrets in the whisper of light. If this journey through the cosmos's hidden blueprint left you awestruck, tap that like button, subscribe for more deep dives into the universe's mysteries, and drop a comment below. Which of these 24 clues reshaped how you see reality? Until our next cosmic adventure, stay curious and never stop wondering what else is written